Good morning to everyone. You've made it to the end of the week. What we're going to do today in class is complete our lecture for flooding, and then we're going to move on to drought before the end of the day today. Um, so where we left off last time was actually talking about channel restoration process. The fact that historically we had sort of widened, deepened, and straightened the channel to try to get water out efficiently to mitigate floods, but that over time we've come to recognize that that's not great for the ecosystems and often not actually better at handling floods in general. And we talked about the fact that particularly in the United States and very locally, right near campus, just west of campus here on the Olentangy, there's been a major channel restoration process that's been ongoing to sort of create more vegetation, which helps sequester carbon, create more vegetation that also provides shade and modulates the temperature, creates a diverse set of bedding scenarios of varying depths and river flow to make sure that ecosystem diversity expands. And in all cases, this process has been a pretty big success. It's now basically finished, probably by the time most of you got to campus. But when I got here, it was very much a work in progress. So clearly, things like along channel restoration is looking at examples of older trees, which of course prevent erosion, but also provide shade and cover in ecosystems as well as nutrients by leaf litter falling into the rivers and things like that. One last flood example I want to talk about before we move on is looking at a pretty catastrophic flood in Colorado in 2013. This is a map here that shows you Colorado. Here's the front range of Colorado, and this actually shows percent precipitation relevant to normal precipitation. And you'll notice that in the front range of Colorado back in September of 2013, you actually saw 600% precipitation above the normal, and that actually was equivalent to I think it was just a few days, about less than a week, in which Colorado experienced more rainfall than it does in its a normal annual rainfall, and created one of the biggest massive flood events in our recorded history. So this is to give you an example of what the stream gauges near Boulder, Colorado did during that time. This is again discharging cubic feet per second over time. So over about a 10-day period, and you'll note that this went, basically, here's an order of magnitude more water than the mean daily statistic for that area. This is almost 500 times what's the normal range of water in that region. 50 times the water was deposited by these rainstorms in that region during that time, which again exceeds the county's annual average in a normal year, all in a devastating period. And just like some of the flood examples I showed you before, of course, the damage is incredibly dramatic. This is a parking lot. I think if I remember correctly, it was a parking lot near one of the regional airports. You can see it was totally filled with sedimentation, flooded. All the vehicles were lost and damaged. In many cases, this led to pretty catastrophic outflows. Obviously, here's a road where policemen and first responders are standing, where the bridge was completely wiped out, and basically nothing left on the side. Other examples where the roads are completely wiped out, and many homes are lost as well. So you think about the impacts of the flooding. Pretty hard to imagine anything in that scenario that wasn't impacted by the flooding. So but miraculously, largely due to the relatively reliable warning systems, only 8 dead, which is not to minimize that incredible loss, but considering the level of flooding is reasonably successful. Although there were tens of thousands of people evacuated, 1,500 homes completely destroyed, many other thousands and thousands damaged, totaling about 30 state highway bridges that were destroyed, 20 that were seriously damaged. And as a result of all this, the infrastructural damages that were being worked on the area, were still active, and I think it was late as 2017 before all the bridges repairs and road repairs were actually completed. Obviously, many of them that can get working partially in the meantime, but there's a major ongoing, or not ongoing now, but it had been a major ongoing response for quite some time. One of the other factors regionally, which is kind of relevant to Ohio, is that there's a lot of oil and gas activity in that region. And one of the things about that is in the new concept of doing hydraulic fracturing, which we'll talk about later in the semester, um, there's often sort of retention ponds near the process. They have the pond there. They put flow back water into the pond, salts and brines and some fracking fluids, as well as massive amounts of water into the brine into these waste ponds. They allow the water to evaporate, or at least partially so, in order to reduce the amount of waste material that has to be taken and either disposed of by discharge or injection to wastewater wells. Um, and obviously, given the mass amount of flooding, most of the waste ponds simply just flooded out. The water was overflowed their banks, and of course got into local soils, in local stream beds in particular. Soils are usually the area because of the fact that they can't really do very well in terms of high amounts of salt content and things like that, where the environmental implications are largely really poor vegetation or sort of salting of the soils in the areas around these waste ponds. So the key concepts I wanted to wrap up on, I'd hope to get to this before the end of last lecture, but I just didn't quite get there. Key concepts I want to talk about in terms of rivers and flooding. Remember, there are two different types of rivers: bedrock and alluvial rivers. Bedrocks, you can see solid rock material, even boulders, gravel in the river channel and in the plain. Alluvial rivers are covered by really fine silt and clay material. The alluvial rivers tend to be much more flat-lying topography. Bedrocks usually have some topography at least over a geographic expanse. And alluvial rivers tend to have very wide channels because of their overland flood deposits. Key term here: drainage basin is the area drained by a single river or river system. These can obviously are particularly important for understanding of the flux of water in and out of certain areas, but also for predicting floods, where if you have a major rain event in a drainage area, in a drainage basin, you can see both flash floods along the tributaries where there's topography, but also you can expect to see major downriver flooding from the fact that the drainage is going to have one drainage area. So the alluvial rivers, again, tend to have a broad floodplain where floods deposit sediments over massive areas. I showed you examples of the Mississippi River where this is on the order of 10 or more kilometers. And often these floodplains are really important to characterize in terms of yearly, decadal, 20-year, 100-year floodplains to get a perspective of the risk of being in those areas. We talked about the flux equation, that Q equals width times depth times flow velocity. And in many cases, there's been a lot of attempts to control river channels using physical approaches of channelization, making it straighter, deeper, constructing levees so if it overflows, it doesn't flow outside the river channel. There's a catch-22 with this, as we talked about, where this does actually help mitigate flooding in certain areas. Which give you the example of St. Louis, where there wasn't as much damage there, but it often leads to upstream and downstream problems where you can't maintain that infrastructure over the entire river, and sometimes flood events are going to exceed the levees, often by the fact that those levees are in place. People's houses and infrastructure were very close to levees, and when that overflows, there can often be more damage than anticipated. So that creates a sort of a bit of challenge. There is a major effort in the United States, particularly in most of the Western countries, to do some restoration of streams and rivers to help alleviate some of the environmental problems. The goal being get more water into the ground, slow the water down by putting in more circuitous paths, and that has the benefit of improving ecosystem health in those areas, but also getting more rainwater into the ground as opposed to having it all go through the discharge regions, which can cause major flood events when rain volumes are too high. So that's going to conclude the discussion of rivers and flooding for the time being. There's some relevant things to this that'll come up later in the semester, but really, again, that's where I'd hope to be at the end of the last lecture. And today we're going to start with kind of a new direction entirely, which is we're going to go the entirely other extreme from flooding and rivers to actually drought in the U.S. We really haven't had any hugely major droughts in Ohio, so perhaps none of you have who live locally have had experienced this. But if you're living in the western part of the United States, anything west of the Rockies, particularly except for maybe the Pacific Northwest, uh, this has been a major issue in the United States. That's becoming exacerbated and quite frankly getting a lot worse. This is one of our core questions going back to the issues of sustainability for thinking about sustainable populations and how to see society survive and thrive. The first stage of these droughts are the fact, of course, that we're seeing below normal rainwater and precipitation, which often can lead to loss of vegetation, salinization of the soils, which can make it really challenging to sort of start to get growth. But the other aspect of this drought is that, of course, increasing global populations put extreme demands on water resources in certain areas. Beyond the fact that climate change, particularly as the El Nino La Nina cycle has changed the weather patterns in the southwestern part of the country. We've seen that part of the nation being an extreme population. That's extreme drought conditions for better part of about 25 to 30 years now. Within the perspective of this class, based on these macroscopic trends of declining volumes of groundwater, declining volumes of precipitation, you might expect from a sustainability perspective that people are making a decision not to move to California or not to move to Phoenix anymore. But in fact, not providing a value judgment on this, but in fact, despite the fact that the water supplies are rapidly declining and really aren't sustainable moving forward, we've actually seen the population of these parts of the country expand pretty dramatically during the same time that water resources are falling off. So it's an area that sort of highlights the really important aspects of the thinking about sustainability of this region. This is an example from a new housing development in outside of Phoenix. You can see just in the upper left-hand corner across the street, this very lush, water-filled homes and greenery. But I'll highlight, I'll just tell you, of course, that's not natural. Does anyone actually know where the water in this part of the country comes from, or where these folks are getting their water supplies? I don't see any guesses there, but most of the water, yep, the Colorado River. That's exactly accurate. So most of the water in this region is actually being accessed from the Colorado River. Dams were put up, the early part of the early part of the 1900s. The Colorado River water was distributed to various cities, and in fact, is a major source of water for folks from in New Mexico, Arizona, Colorado itself, Utah, and California, Nevada. And as a result, we've basically taken an area that has, that actually is designed to look like this, although it's gotten drier in the last 25 years than average. And we're using Colorado River water to actually increase the vegetation and the hydration of the soils in this area. So I sort of love this picture where, you just arbitrarily pick a new plot of land out in the middle of the desert and build this mega home with a big pool and water without any capacity to really sustain it unless you're getting water from the Colorado. We'll get into the Colorado River discussion later in the semester here, but basically that water's been partitioned out to the point now that on the vast majority of years, water doesn't even reach the Pacific Ocean anymore. But there's specific allotments of water to each of the states and to Mexico. But it's a major water crisis across the country. So I'll call your attention to this. This is this week's U.S. Drought Monitor for the United States. It's actually done by University of Nebraska Lincoln. If you're living in Ohio, you've seen that even though the summer was quite dry, you've seen the fall here get a little wetter. We've seen that there's no sort of deficits of water in the region, and things are kind of fairly normal for us, specifically since the tropical storm season's brought some storms up the Mississippi and Ohio River valleys and stuff like that. But look at the sort of the Great Plains, the middle part of the country, and the west in the Rockies, and you'll see here that the vast majority of the rest of the country actually has one of these designations of either yellow being abnormally dry, tan being moderately dry, dark, dark light brown severe drought, all the way to red and I don't know what that's actually called, but dark red, extreme drought, exceptional drought. So particularly look at this area through Colorado, Nevada. This is basically called the Basin and Range provenance and the Colorado Plateau provenance that are at extreme, exceptional drought. An exceptional drought is a level of drought. Um, uh, this isn't the formal definition, but exceptional level of drought where you've actually seen a reduction of surface water resources. You can assume most of the streams, the Colorado still flows. Most of the streams in the area are now dry river channels. And during exceptional drought conditions, you also start to see loss of vegetation. So not only is it impossible to grow agricultural crops in most of these situations, we actually see that the natural vegetation starts to severely suffer because of the water table actually drops below the level of the roots, and it's impossible to keep creating water. So one of the things I was going to talk to you about a little bit today is that this region of drought's been extended for about 30 years now, 25 to 30 years, where this black outline in here is the Colorado Plateau. And that Colorado Plateau is just a provenance of geology where there's an old sort of microplate that got created in the United States. It's important because it has high elevation, so it's sort of what we would call a montane desert or a high altitude desert, largely speaking. So it's normally in dry conditions, but now it's exceptionally dry. And if any of you have been following this in the news, it's actually one of my biggest, my lab and um, my main job at Ohio State is actually handling certain aspects of this. I'll talk about in a second. But in light of this long-term water issues, there's major concerns in the region about water poverty. There's actually such a little amount of water accessible in this region that people are being impacted both economically and health-wise from the fact that there's not enough water to drink, and there's major concerns about water security. So if you're thinking about this from American citizens, if you're thinking of this as an American citizen living in Albuquerque or wherever the case may be, this is a major concern on a macroscopic scale, but most folks are just getting their water from the Colorado or the Little Colorado River that comes through here, and basically there's water that's distributed around. If you've been watching the news recently, right in this part of the country is actually the Navajo Nation reservation, and they don't actually have a significant proportion of Colorado River or Little Colorado River water sort of allotments. As a result, they've been severely affected to the point of having major water poverty and have very discrete water security issues in the sense that the average person living in a rural area has to drive, on the order of about 10 miles to a centralized water source, usually, in a pickup truck with a tank on the back of it, and actually has to get the water in a localized area. So now this concern about water poverty and water security has been ongoing for a while in light of drought, in light of drought that's been made more extreme by climate change. But the issue is that earlier this year, during COVID times, where people were driving these centralized chapter houses, which are actually kind of similar to county seats in an area like Ohio, to get their water from centralized facility, it became a major spreading center for COVID. So our work at Ohio State, particularly through the Global Water Institute at Ohio State, has been trying to develop a sustainable village water systems model to basically provide water in the region, which the first goal that would be providing water from solar powered pumps. So there's no pollution, or carbon footprint of this water supply. Developing water treatment systems and actually purify this water to a level that can be used for agriculture, for livestock, and for drinking. And then along with that water, provide sort of training and education modules upon best ways to get water out of the ground, best ways to make sure your water supplies are sustainable, and also to develop WASH, or water sanitation and hygiene, as well as agricultural training modules that folks can actually start to use the water in a meaningful way. So just give you some idea of the pictures here. This is one of the more rare examples of an actual sort of farm pump. Um, this is a man named Dr. Rudy Shabala, who's actually the director of natural resources in the Navajo Nation, and he's hand cranking this water um, just to feed his goats. He has to hand crank this pump about 2,500 times a day. So one of the goals is just to try to put in solar powered pumps in areas to get water out more efficiently, so people don't have to spend so much of their day getting water. You can imagine the impact on your ability to work or grow crops or do other things if you're pumping water for a few hours a day. And I'll talk about this more as we go through the semester, but it's not. I mean, what's happening there in the Navajo Nation is horrible, but it's not unique in the world, right? There are areas that I work in Tanzania where women are spending, 2 to 4 hours a day carrying pumps, tanks of water, carrying empty tanks to get water, and then carrying 100 pounds of water in their back just to have drinking water. So the issues of drought, and aridity, and particularly the impact of drought and aridity in areas that are exacerbated by climate change are really important, and actually probably affect about 2 billion people on our planet, which is a really large proportion of our society. So we're quite blessed here in the U.S. in general. So this is another example from our trip to Navajo, looking at the sort of infrastructure around this area for water, which has been damaged over time, hasn't been replaced, repaired very well. And this is actually a location where there's some of the wild horses on the Colorado Plateau come. So normally this is a windmill, feeds water, and the water sort of spills out slowly, and the horses come in desert oasis for great distances to get the water. The drought, as it's been that extreme drought for a prolonged period of time, has gotten to the point where not only does this water not flow all the time, but because the water for aquifer has dropped down, but the windmills also actually been broken in this particular instance. And just sad to say, but just to show your perspective here, there's actually an example of some of the dead wild horses. So this is, if you see, the vegetation is almost down to nothing. This is a high altitude desert where there's some vegetation normally. 25 years of extreme drought, most of the sort of surface vegetation has been gone. This obviously changes things like erosion, but it has some pretty extreme situations like this. But we were actually able to see some wild horses in the region. They still make their way into this area where there's water around. And I'll show you a brief video here, just to hopefully everybody will be able to hear this, just to show you the effort and what's happening in that area.
My name is Rudy R. Shabala. I'm a Navajo Indian, and I'm also the executive director for the Navajo Nation Division of Natural Resources. We're looking at this particular water source where it dried up, and the livestock, they died of thirst, and the equipment's not functioning. And we've been in drought for quite some time, and our forage is really decreased. Yesterday, we were in the western part of the Navajo Reservation, and we visited a particular hand pump water well where the livestock producers, it's the only water source within 7 miles in each direction. And it's a hand pump water well that never dries up. The people that bring their livestock there, they hand pump the water troughs full of water. The water pumps, the windmills out in the field, out in the ranges, A lot of them are in disrepair. We started relying on the water source from the chapter houses more. My concern 3 years ago was what if something happened? We should have these windmills and hand pump water wells in operable conditions, which is indeed what happened when the COVID-19 struck. And when the chapter shut down, the water sources were cut off. The people that live out in the country that call
That's an
their water
example.
every day, all of
That's an example of sort of the best case scenario for water. Dr. Shabala mentioned a 7 mile trip. You saw the Navajo woman and her daughter carrying jugs of water, back to their homes for that day's drinking water. But folks who want to try to have agriculture, or try to have livestock, they come maybe once or twice a week to these centralized chapter houses and fill up a tank and haul back. But you can see the incredible infrastructure you have to have to get the water. On a global scale, when we think about providing water resources to individuals, we tend to think about a price per gallon of water. Maybe 1 to 2 cents per gallon is an economic price to have sustainable water supplies. Your municipal water supplies in places like Columbus. If you look at the price per gallon, it's actually probably cheaper than that in most cases. Here it's actually almost measured in the price per gallon has to include the miles per gallon of your vehicle to transport water around if you want to do anything sort of meaningful besides, with agriculture, anything industrial, I should say, to move any meaningful volumes of water around. So it's quite striking to recognize.
Suddenly they were without water. Water is life is a statement started by grassroots people, if you will, that live out and make their living with livestock, make their living with their gardens, dependent on water. You can dodge COVID-19 by social distancing, by staying home, by wearing masks. But you can't dodge being without water. You can only live for 3 days without water. And so water is life. One of the main problems that would be solved with water spread out throughout Navajo country, it allows people to stay home to attend to other duties rather than have to be in line waiting at the chapter house for water. If they have a water source that's reliable nearby, all the families in that area can safely know that they have a water source nearby for themselves, their livestock, and for their gardens.
So hopefully that gives, it's quite a sad situation, but hopefully gives you a sense of just how dire the water needs are in that region, and just how serious the issues of drought can get, particularly over prolonged periods of drought. Obviously, I mentioned 2 billion people suffering from water poverty and without water security in the world. It's billion with a B. It's quite amazing to recognize that many in the country of Africa, subcontinent of India, as well as large regions of Central and South America, which are largely together called the Global South, the area of. I'll put some of this information on the web on the Carmen page, but many in the Southern Hemisphere in particular actually live without sort of access to modern water infrastructure, and as a result of changing climate in particular, have experienced local drought. So if you're interested in this kind of work, you can look at the Global Water Institute webpage. That's sort of my main job these days. But if you're interested in getting involved in more work like this, there's plenty of opportunities for research and stuff like that. So feel free to look it up and contact the GWI about those activities. Moving on from these particular examples, there are other regions of the country that have prolonged extreme droughts. Many of you've probably heard about the areas, the severe water shortages in California. The water shortage in California can affect millions of people in the state. Nearly 40 million people in the region are also living in sort of with a lack of water security. This part of the country, in addition to having incredibly large populations, has gotten a lot of attention because of the incredible amount of agriculture that actually occurs in the Long Valley or the Central Valley of California. Um, so the example I'm going to talk about here is really from up to about September 2015, where the extreme drought got to the point where water reservoirs were being emptied across the state, where the groundwater was so depleted that there's actually about a foot of subsidence a year, where the ground was actually, based on the fact that the water was no longer in the pore spaces in the ground. When the water is pumped out, the ground actually compacts. There's a subsidence, and for quite some time, recently about 2015, 16, there was major concerns whether we were going to be able to provide enough water for this region of the world. In a very developed locations in California. There was a major episode of high rain in, I think, about 2017 that mitigated some of these concerns for a period of time. But as you can see, even after an incredible rain event, 2017, we'll talk about later in this next week. There's still, most of the state is within some amount of drought concern, particularly the northern part of the state, where of course you've heard a lot about in the last few years regarding the forest fires and things like that, are still in extreme drought in the area. So one of the things I want to set this up is just thinking, where does California's water come from? So for the record, California's water system serves over 50 million people. So that's a huge component of the U.S. population in comparison. This one of the main uses of that water is not just for drinking water, but actually for the irrigation of about 5.5 million acres of farmland in the area. This in the High Plains or the Great Plains region east of the Rockies are two of the biggest, most important agricultural regions in the world. About 25% of a lot of vegetables grown in the United States are grown in this area. So if you're eating things like blueberries or almonds and broccoli and stuff like that, a lot of that's grown in that region. And for perspective, 80% of all that water used in California, it actually goes for agriculture. So it's not just the people living there. It's actually that most of it's used to keep feeding the U.S. and U.S. exports. So agriculture is a really important part of this California water problem. In the Central Valley, which is the region right through the sort of center of California where most of this agriculture occurs, 17% of the land is 17% of all the land irrigated in the United States is within the Central Valley. Most of it is sort of what's called pivot irrigation. They drill a well. They have these circle crops, circle irrigators that spray the water down, or more commonly in California, they actually have water wells that pump into a distribution pipeline that distributes the water into irrigation ditches, or either in ditches or into pipes in more precision irrigation to provide water across the agriculture area. And that Central Valley region of California, again, produces 25% of the U.S. food, and is also a major area of agricultural export out of the United States, which obviously is important for the U.S. economy. So in the region, there's really two main sources. They're not going to differ no matter where you go, right? Effectively, both are used in California, and that's going to be groundwater, water pumped from the ground, typically by wells. Some cases, very rare cases, these can be found in artesian springs. In that part of the world, it's all from groundwater. And surface water. Surface water is a mixture, as we talked about earlier in the discussion of the hydrologic cycle, is a mixture of water that falls by precipitation. It could be snow, rain, or it can also be related to snow melt. In California in particular, snowpack and snow melt are major sources of surface water. And the last component, of course, is, as you can see in California, in the case of the Colorado River, is that an additional source of surface water is river water that fell by one of those processes upstream in the Colorado area of the Rocky Mountains, in the case of the Colorado River. So Just to get you oriented here in California, groundwater accounts for about 30% of the water supply during normal conditions. Of course, um, just like other parts of the world, when you see prolonged periods of drought, the water tables will drop as water is being used and less water is coming in. But the effect of surface area is dramatically greater in periods of drought, where you start seeing, the plants want to continue to survive, so they're going to continue their evapotranspiration processes. The surface water, the soils, and the shallow groundwater will be depleted. The water will be lost to keep the plants alive for as long as that can go on. But at some point in time, with the absence of new sources of, either river inputs, snowpack melt, or rain, the surface water component of this sort of gets lost, and at that point in time, groundwater often will become a much bigger component for mitigating drought concerns. So I'll give you an example of that extreme drought I talked about in the Navajo Nation. It's probably more like 90% of the water comes from groundwater, and even higher for drinking water purposes in that region. So, but it can be quite high, up to 60% in areas like California. And one of the things that in the sort of modern world is, in light of engineering and sort of infrastructure development, surface water now has to include reservoirs, and the waters in present rivers, because you're more likely basically trying to harvest that surface water coming down through rivers and collect it into reservoirs and store it for, we hope to store it for longer periods of time. So we need to consider, particularly in areas with agriculture, with infrastructural development around water, like California, reservoirs are major components of surface water. Obviously, in the poorer nations in the global South, Central South America, Africa, for example, most of the Middle East, there isn't nearly as much infrastructure around this. The reservoirs aren't as common, so they're not really there to buffer changes in water levels and water access. So just give you a sense of the reservoirs and water distribution in California. This is a whole line of major reservoirs. You can look at the size of the block of the square is proportional to the reservoir capacity. This is the California. This is the Bay Area, San Francisco. This is San Diego, Los Angeles, and you can see here that most of the reservoirs are actually up, in the eastern mountains of the mountain belt on the eastern side of California. This is the Central Valley in the middle here, and a big component of the reservoirs are providing water down into the irrigation for the Central Valley. They also have this canal aqueduct system that distributes water to all parts of the Southern California. San Diego, LA, exist almost entirely on water that comes down from either precipitation or snow melt in the Sierra Nevadas in this part of California. So additionally, for Southern California, particularly for Southern LA and San Diego, there's another major aqueduct that brings water over from the Colorado River. So the Colorado River would normally sort of form the eastern boundary of California and Arizona, I suppose, and then go on to Mexico. But major component of the water use is to actually sort of irrigate or aqueduct the water from the Colorado over to Southern California. So most of the, LA actually gets water from both the Sierra Nevadas and the Colorado River. The scary thing we mentioned recently is 2015, is that these reservoirs were in many cases, getting to some of their lowest levels in recorded history. Or the capacity of these reservoirs are, of course, shown in the big bar, and the water levels were significantly below both the historical averages, but also well below what we'd like to see in the reservoirs. So they got to the point of 10% of their capacity, major decreases in the reservoirs. People living near the reservoirs were quite concerned about that they once upon a time were living on a lake or a body of water. Now they're living on, a gully with water at the bottom. But it got pretty serious in the sense there just wasn't a lot of capacity left to um, provide water in those in California. So um, right before the major rain event where we had a rainy season in California for about the first time in 20 some years there, the drought effects are pretty serious. The reservoirs in the state were about 28% of the state's capacity. Um, Things like hydroelectric power generation were 30% below the recent average and about 60% below the long-term average. And the reason why the reservoirs are so low actually had quite a few reasons. It's relatively complex. It wasn't just simply drought, but we'll go through this here in order. So the biggest aspect is this sort of long-term issues related to climate change and related to precipitation distribution in the area, which is that the baseline of which California's water supply has been developed or was developed upon was based upon accessing surface water from snow melt in the Sierra Nevadas. And about 2017, this is at a 500-year low of snow melt, of snowpack in the Sierra Nevadas, as well as snow melt discharging down seasonally into recharging the reservoirs that provide water to the region. Obviously, you can imagine that with climate change, as climate continues to warm, this snowpack is going to decrease, and I think we all would recognize that at some point there's a genuine risk that snowpack would simply be lost if climate warmed significantly enough, which could create bigger concerns long term for Californians. So how has the snowpack been calculated? Obviously, people weren't recording the volume of ice 500 years ago in that part of the world, but the way it's done is actually using California blue oak trees, looking at tree rings, and they provide the growth of the tree rings provide an indicator of water content, which we tied to snowpack and snow equivalent for back sequentially for years, and basically what they've seen is a drop off relatively recently, from that trend. For perspective here, this is just by no means is the before case here a example of a great amount of snow in the Sierra Nevadas. Snowpack had already been falling in this region by this time, but this is the snowpack in 2010. That amount of meltwater was each year, into the reservoirs that are seated along this margin of the western margin of Sierra Nevadas. That was enough to basically keep most of California's agriculture and water needs in balance. You notice that it would allow for natural vegetation in the Central Valley, and then the rest of this area actually becomes quite green as it becomes irrigated with the water, with snowmelt and during agricultural year. But notice by 2015, this snowpack had dropped dramatically. Again, warmer climates, lower precipitation. If you're not adding more snow, you're losing it to sublimation, to directly by solar heating and by melting into the river, into the reservoir systems, and as rivers to the reservoir systems as well. But as a result, by March 2015 and up until the extremely wet year we had in 2017, the snowpack was rapidly decreasing, and it wasn't very clear how we were going to sort of correct this water problem in that area. So this became a major political issue. I believe it was the governor of California at the time, with the folks from the USGS and Water Resource Division trying to placate the public and present a plan. But in addition to this lack of snowpack, California was also experiencing a huge rainfall deficit. Clearly, the lack of snow was one of the main components of the lack of precipitation led to a lack of snow as well, and that partly led to the lack of the decrease in the snowpack. But across the region, rain patterns, rainfall was down. The patterns were bringing these rainfall patterns going further to the north. So you have this thing called the El Nino and La Nina, which we introduced a bit earlier on in the semester, but I'll talk about more as we get to rainfall later. The theory is that as climate change intensifies, as the planet becomes warmer, the water that used to get evaporated in the southern Pacific would sort of blow up. The storms would blow through southwestern United States in a sort of monsoon-like rainfall. Places like California, San Francisco, California, but have predictable rain every October, November kind of time frame. Seattle and stuff would get this as well. But the theory is that as climate change increases, these rainfall patterns will go further to the north, and actually you're no longer seeing that precipitation fall across the southwestern part of the country. Um, on a 4-year average, there were major deficits of rain compared to the norm in that region. So the normal is again is tailored to the location, the amount of rainfall that's been the long-term average. Values are given in inches, and some regions need, to be clear, some regions in that 4-year period at the back end of a 20-year drought had such severe deficits, 68%, 52%. They would need they basically needed 2 full years of rainfall just to get back to norm. Just get the precipitation rates back to the normal amount in the region. The third factor, so snowpack being first, snowpack decreases being first, rainfall being second. The third factor is that, over the long term, as the agricultural activity in the Central Valley has expanded, you are seeing groundwater use increase and increase and increase, right? When there's a drought period, we sort of go to the groundwater. Why? Hopefully, most of this seems intuitive, but the water in the ground might drop because less water is coming in, but by and large, it's not evaporating, it's not being lost, and it's basically creates a water store or a water bank. People often call water banking, intentionally letting water be recharged, or in many cases of California, there's actually a strategy called managed aquifer recharge, where they come to some of those areas of reservoirs in wet years, and they literally pump water down into the ground or into irrigation, into groundwater systems and down near the irrigation fields, and try to bring the aquifers levels back up so that there's less likelihood, or that there's more water there when they need it. So there's less likelihood to be without water if they have to rely on groundwater. But as a result of the cumulative change of the pumping water in areas in times of drought within areas of the Central Valley, you actually saw the groundwater was being depleted quite dramatically. This is the gray satellite. This gives you a sense of water levels in the soil and in the surface of this area, and all of them showed a trend towards decreasing levels of water, in that region. Part of this issue with pumping the groundwater, as I mentioned earlier, is that as you continue to pump water out of the groundwater, you can see these long-term depletions of the aquifer. So this is the Sacramento Valley up to the north. You notice that it's been sort of hovering along and decreasing just recently, but the San Joaquin Valley in the central California over time has been pumped down steadily to a decline of about 15 to 20 feet in the acre feet of the aquifer has been down. So the aquifer is dropping, basically 25 foot in a given area. And then the Tulare Basin, north of LA here, I guess sort of south central or central California, that area has been in a prolonged period of drought. Basically, if you wanted to be blunt about this, they just never had enough groundwater or surface water resources to allow for the amount of agricultural development that occurred. And as a result, this has been depleted almost instantly from the beginning, and is now actually down almost 125 feet below the background levels of aquifers in the region. So these are major decreases in drawdown. So it was only recently as 2014 that the legislation governing groundwater was enacted to try to correct and mitigate some of these things. If you've heard the phrase, it's the joke about California water is whiskey's for drinking and water's for fighting over, and it took a long time to sort of get the legislation aligned. But the reality is this is quite important, because during that same period, because of the lack of surface water, there was a need for actually increasing number of new well permits, people trying to get into the groundwater to get their water to sustain the water they didn't have from surface regions. So key thing we'll end here is that the net result here is you think about these rocks in the subsurface, these sediments in some cases having about 30% pore spaces in them. So 30% of the rock is the space between it, and that space can be filled by water. That space is called porosity. If I didn't say that, and groundwater is pumped from those pore spaces for agriculture or drinking water. What happens in these areas again is that as you pump down the water, the water table drops. The area above it, the pore spaces, when they're filled with water, actually keep the sediments apart and actually preserve the pore spaces there. Over periods of time, when that's gone, the weight of the rock itself actually causes the rock or the sediments to actually, more accurately, the sediments to compress or compact, and that compaction doesn't just cause shrinking or doesn't just cause sinking of the sediments as we observe from the surface, where the land is sinking and sinking and sinking. It also reduces that pore space permanently. So even importantly in this area, once those sediments are filled with water, or says that were filled with water, are lost, and that pore space is gone by compaction, the next rain event actually doesn't allow the pore space back open. That space is lost forever, and the lack of that pore spaces actually prevents water from recharging into the ground. So for starters, that's bad for the future of groundwater resources in the area. But if you're there during a major rain event, that's also really bad because there's a higher incidence of flooding in those regions. So it's a situation there from a sustainability perspective. The cat's already out of the bag. But particularly in Tular and San Joaquin basins, we're already seeing sinking by nearly a foot per year, which is incredible. Imagine building a house and knowing that every year your land surface is going to drop by a foot. When you think about the kind of problems this can cause, obviously infrastructure damage. You can break water pipes, gas lines, things like that. It's not very different from an earthquake. Many of the irrigation canals people built to get water off the irrigation plant and irrigate a field have now actually found they've subsided to the point where the water is flowing out of the field back to the irrigation ditch. The bottom line is, I'll end there, but just to state that the future of water resources in California is something that requires an incredible amount of work and a lot of attention. And probably at this point, there's still many more questions than answers, although a lot of it's been mitigated by extremely wet year in 2017. I think we covered a lot of ground today. We got behind about a lecture behind schedule here, but I'll try to get us back on target. Just remember that the last rivers worksheet is due tonight, and there'll be a new worksheet posted on Sunday. I hope you all have a great weekend. Enjoy the return of Big Ten football. Sorry you all can't get the opportunity to be there if you're fans, but I hope you all have a great weekend, and thank you for listening along.